Hey, my friend. Tonight, we're stepping into the quieter corners of Einstein's mind. Not the famous time dilation or the sweeping curves of space-time you've heard before, but the hidden, forgotten theories that still shape how we understand the universe. So get comfortable, let the world slow down around you, and let's explore together. Chapter 1. The Photoelectric Effect, when light acts like particles. The name Albert Einstein often conjures images of the theory of relativity, the bending of space-time, and the slowing of clocks near massive stars. These ideas reshaped our view of the universe so completely that they tend to eclipse much of his other work. Yet Einstein's career was filled with insights beyond relativity, spanning quantum theory, statistical mechanics, cosmology, and even proposals for new states of matter. Some of these ideas were so far ahead of their time that they were not fully appreciated until decades later. Others were recognized immediately, yet became overshadowed in the public imagination. Among these so-called forgotten ideas, one stands out not only for its historical importance, but also for the way it quietly launched the quantum revolution. His explanation of the photoelectric effect. The photoelectric effect's puzzle began as a technical curiosity. When light shines on certain metals, it can cause electrons to be emitted from the surface. This phenomenon had been observed as early as the late 19th century. But its behavior stubbornly refused to align with the classical wave theory of light. If light were simply a wave of electromagnetic energy, the intensity, the brightness, should directly determine the energy given to the electrons. Brighter light should make electrons fly out faster. Yet careful experiments showed this was not the case. The energy of the emitted electrons depended solely on the light's frequency or color, and not on its brightness. Even a brilliant red light could fail to produce a single electron if its frequency was too low, while a faint ultraviolet beam could knock electrons out instantly. Physicists attempted to reconcile this with the wave model by suggesting that electrons might need time to accumulate energy from the light wave. In this picture, a sufficiently bright beam should eventually release electrons, no matter the frequency, if one simply waited long enough. But experiments destroyed this idea. The emission of electrons was effectively instantaneous for high-frequency light, even at the lowest intensities. There was no measurable delay, no gradual charging up of the electrons. This was the first clear hint that the interaction between light and matter operated on principles far stranger than classical physics could account for. Einstein's leap came in 1905, the same year he published his special theory of relativity. Building on Max Planck's quantization of energy in blackbody radiation, Einstein proposed that light itself was made up of discrete packets of energy, later called photons. Planck had used quantization as a mathematical device, never fully claiming that light was literally particle-like in nature. Einstein, however, treated these quanta as physically real. In his picture, each photon carries an energy proportional to its frequency. When such a photon strikes a metal, it interacts with a single electron. If the photon's energy exceeds the work function, the minimum binding energy holding the electron in the metal, the electron is ejected. The excess energy appears as the kinetic energy of the outgoing electron. If the photon's energy is less than the work function, no ejection occurs, regardless of how many photons strike the surface. This model explained all the perplexing features of the photoelectric effect in one stroke. The threshold frequency corresponded to photons with just enough energy to overcome the work function. The kinetic energy of the emitted electrons increased with light frequency because higher frequency photons carried more energy. The intensity of the light controlled only the number of photons striking the surface, and thus the number of electrons ejected, but not their individual energies. The simplicity of Einstein's explanation belied its radical nature. The scientific community was slow to accept the photon concept, even as experiments piled up in its favor. Robert Millikan's decade-long experimental program measured the energies of photoelectrons with great precision by applying a retarding voltage that just prevented them from reaching a detector. The voltage required to stop the electrons traced a straight line when plotted against the light's frequency, with a slope revealing a fundamental constant and an offset tied to the material's work function. Ironically, Millikan began the project convinced that the photon idea was wrong. His meticulous data forced him to change his mind. In 1921, Einstein received the Nobel Prize for this work, a recognition that the quantization of light had moved from bold hypothesis to bedrock. To appreciate the depth of the shift, it helps to recall what came before. Light had been the archetypal wave. Interference and diffraction experiments painted vivid patterns that only waves could explain. The photoelectric effect did not erase those patterns. It added a new layer. Light could behave like a continuous wave in one experiment and like a stream of indivisible packets in another. The two faces were not contradictory so much as complementary, each emerging under different conditions. This dual character would soon be generalized to matter itself, when electrons were shown to diffract like waves, and atoms were understood through standing wave patterns. The photoelectric effect was an early crack in a wall that soon gave way to a new architecture of physics. Although the essence is simple, one photon liberating one electron, the details in real materials are rich. The energy needed to remove an electron is not a universal number. It depends on the metal, on how its atoms are arranged, and even on the condition of the surface. Alkali metals with loosely bound outer electrons tend to have lower work functions and therefore respond to longer wavelength light, whereas many noble metals require higher frequency illumination. Surface contamination can raise the effective barrier noticeably. A monolayer of adsorbed gas may be enough to suppress emission. Experimentalists learn to polish, clean, and heat surfaces in vacuum to obtain reproducible results. They also found that roughness, crystal orientation, and surface chemistry all subtly shape the yield and angular distribution of the emitted electrons. A practical way to probe these energies is to vary a stopping voltage until the photoelectric current vanishes, which reveals the maximum kinetic energy of the most energetic electrons. Doing this across many light frequencies maps out the linear relationship that was the smoking gun for Einstein's interpretation. The intercept of that line depends on the work function, so two metals illuminated by the same color of light can produce electrons with different kinetic energies. That sensitivity turned photoemission into a materials probe. Over the 20th century, it evolved into photoemission spectroscopy, in which the energies and angles of the escaping electrons are measured so precisely that they reveal the underlying electronic structure of the solid. Angle-resolved photoemission spectroscopy, often called RPS, goes a step further by reconstructing how electrons move inside a crystal, band by band. Because an electron carries momentum as well as energy, tracking the directions in which photoelectrons emerge helps map the quantum landscape within the material. In ordinary metals, this shows broad, simple bands. In more exotic systems, such as high-temperature superconductors or materials with topological surface states, the maps display intricate features that signal new kinds of order or protected conducting channels. In this way, a phenomenon first used to test the nature of light became a precision microscope for the hidden architecture of matter. Ultrafast lasers have pushed photoemission into the realm of time. Pulses lasting femtoseconds and even attoseconds act like strobe lights for electrons, allowing researchers to watch the very first instance after a photon is absorbed. In pump-probe experiments, one pulse excites the system, and a delayed pulse ejects electrons, whose energies encode how the system has evolved in the tiny interval between pulses. These techniques reveal how quickly electrons share energy with each other and with the vibrating lattice, how transient states arise and disappear, and how collective excitations leave fingerprints on the spectra. They also expose regimes in which more than one photon contributes to emission, a nonlinear process that becomes likely when the light is very intense. Multiphoton photoemission, far from contradicting Einstein's picture, extends it. An electron can absorb two or more quanta in rapid succession and depart with a correspondingly larger energy. The momentum side of the story matters too. Photons carry momentum, and conservation laws must be respected when an electron absorbs light and escapes. In a gas, the momentum balance is simple. In a solid, the crystal lattice acts as a silent partner, accepting or supplying the small difference so that the electron can find a path out. This is one reason surfaces and interfaces demand care. The escape process is often described in 3 steps: excitation by light, migration to the surface, and transmission through the surface barrier. Each step has its own inefficiencies and dependencies. A clean, ordered surface helps. So does choosing photon energies that penetrate just enough to excite electrons near the surface, while still leaving them with sufficient energy to cross the barrier. Not all photoelectric devices operate by ejecting electrons into a vacuum. In the internal photoelectric effect, the light promotes electrons from bound, non-conducting states to mobile states within a solid. Photodiodes and solar cells exploit this by building electric fields into semiconductor junctions that separate the newly mobile charges and send them into a circuit. The internal and external effects share the same quantum origin: the transfer of a discrete packet of energy from light to an electron, but differ in what happens next. This duality of mechanisms is reflected across technologies, from image intensifiers that rely on vacuum photoemission to the deep stacks of doped silicon that harvest sunlight on rooftops. Practical engineering has refined these ideas into robust tools. Photocathodes are chosen for sensitivity in a desired spectral band, often trading durability for low work function. Cesium-based compounds respond well to visible light but require careful handling. Robust metals can be simpler to maintain but usually demand ultraviolet illumination. Designers also grapple with space charge effects. When many electrons are emitted in a short burst, they repel one another and can limit current or blur timing. Carefully shaped electrodes, high vacuum, and pulsed operation help to mitigate these constraints. Even reflectivity matters. As frequency rises, many metals reflect more strongly, which can reduce the fraction of photons that penetrate far enough to do useful work. Coatings and surface texturing can recover some of that lost absorption. Historically, the photoelectric effect linked communities that did not at first speak the same scientific language. Researchers of light and researchers of matter learned to see their subjects as 2 halves of a single conversation. The recognition that light can act like a particle made it easier to accept that particles might act like waves, a symmetry of perspective that soon found dramatic expression in electron interference and in the nascent quantum mechanics of atoms and molecules. The cultural shift in physics, the willingness to take probability, quanta, and complementarity seriously, owes much to the clarity of this one phenomenon. Einstein's own attitude toward the quantum world remained cautious, even as the photoelectric effect helped build it. He accepted that the energy in light is granular and that chance appears at the point of measurement, yet he wondered whether apparent randomness hides deeper structure. His later work with colleagues on thought experiments about separated particles, meant to probe the completeness of quantum theory, echoed the same desire for a description of nature that felt continuous and causal. It is striking that the scientist who gave one of the most decisive early arguments for the quantization of light also pressed the field to clarify what, exactly, a quantum description claims about reality. The effect's reach continues to grow. In chemistry, ultraviolet photoelectron spectroscopy measures how tightly electrons are bound in molecules, helping to identify substances and understand reactions. In surface science, X-ray photoelectron spectroscopy determines which elements are present and what chemical states they occupy, a staple of materials analysis from batteries to catalysts. In astronomy, photoelectric detectors have made possible space telescopes and instruments that count individual photons with exquisite timing, letting us measure faint signals from distant sources. In quantum information science, single-photon detectors built on internal photoelectric principles register the feeblest glimmers, enabling secure communication protocols that depend on the indivisibility of light. Another thread in Einstein's work ties directly to the photoelectric story. A decade after his 1905 paper, he introduced a simple statistical model for how atoms absorb and emit light, complete with coefficients that quantify spontaneous and stimulated processes. Those ideas anticipated the principle of stimulated emission that makes lasers possible. Although lasers rely on carefully prepared populations of excited atoms rather than on photoemission from metals, the conceptual through line is unmistakable. Light exchanges energy with matter in quantized steps, and by arranging the steps carefully, we can coax nature into doing precise optical work. The seeds of that control were visible in the photoelectric effect long before the word laser was coined. Seen from today's vantage point, the photoelectric effect feels inevitable, as if the world could not have been otherwise. But before the shift, many clever people had good reasons to believe the wave picture was complete. It took an imaginative leap to suggest that the graininess first glimpsed in the heat radiation of hot objects was not an artifact of calculation, but a trait of nature itself. In that leap, a century of new physics found its foothold. The world, it turned out, is hospitable to both waves and quanta, and it invites us to choose the right language for the right question. There is a quiet beauty in the fact that a simple observation, light striking a piece of metal and producing an electric current, could lead to a profound change in how we understand reality. It reminds us that the universe often hides its deepest truths in ordinary phenomena, waiting for the right kind of attention. And there is a soft existential echo here too. If light itself arrives in indivisible steps, perhaps our understanding does as well. Long periods of continuity punctuated by sudden clarity, moments when a threshold is crossed and the world is never quite the same again. Chapter 2. Relativity of Simultaneity. Why now depends on who you ask. When we think of time, we tend to imagine it as a universal backdrop, the same for everyone, ticking away at the same rate no matter where you are or how you move. This idea feels so obvious that for centuries it went unquestioned. It is woven into language and daily life. When we say something happened at the same time as something else, we assume there is one shared clock by which the entire universe can keep score. Yet one of Einstein's most surprising insights in his special theory of relativity is that simultaneity, the notion of events occurring at the same moment, is not an absolute truth. Instead, it is dependent on the motion of the observer. What is now for one person may not be now for another. The seeds of this realization were sown in the early 20th century, when physicists struggled to reconcile the newly formulated laws of electromagnetism with the framework of Newtonian mechanics. Maxwell's equations, which describe the behavior of electric and magnetic fields, predicted that light should always travel through a vacuum at the same speed, regardless of the motion of the source. This clashed with the Newtonian expectation that speeds should simply add and subtract depending on relative motion. If you are walking on a train moving forward, your speed relative to the ground is your walking speed plus the train's speed. Classical physics assumed light should behave the same way. A crucial experiment by Albert Michelson and Edward Morley in 1887 tried to detect differences in the speed of light depending on the Earth's motion through space. The result was a shock. No difference was found, no matter the orientation or timing of the experiment. The speed of light appeared to be constant in all directions, a result that seemed incompatible with the idea of a fixed, universal time. This puzzle set the stage for Einstein's 1905 formulation of special relativity, which took the constancy of the speed of light as a fundamental postulate and reshaped our understanding of space and time to make it work. The relativity of simultaneity emerges naturally from this framework. Imagine two lightning bolts striking the front and back of a moving train. From the perspective of an observer standing on the platform, the bolts strike at exactly the same time. This could be confirmed by placing detectors at the front and back, each connected by wires to a clock at the center, and checking that both signals arrive simultaneously. However, for a passenger sitting at the train's midpoint, the situation looks different. Because the train is moving forward, the passenger is moving toward the spot where the front lightning strike occurred and away from the spot where the rear strike occurred. Even though light travels at the same speed in all directions, the light from the front strike has a shorter distance to cover to reach the passenger, while the light from the rear strike has farther to go. The passenger will therefore see the flash from the front before the flash from the back and conclude that the front strike happened first. Both observers are correct in their own frames of reference. There is no privileged perspective. This thought experiment reveals a deep truth. Simultaneity is relative. The concept of two events happening at the same time only makes sense within a single frame of reference. Change your motion, and you change your judgment about the timing of distant events. Importantly, this effect is not due to differences in perception or delays in signals caused by imperfect measurements. It is built into the very structure of space-time. The mathematical backbone of this result is the Lorentz transformation, which relates the coordinates of events in one inertial frame to those in another moving at a constant velocity. These transformations show that the time coordinate of an event is not independent of its position. Change the velocity between frames, and time and space coordinates mix. This mixing is why observers in relative motion will disagree about whether two spatially separated events are simultaneous. The effect is negligible at everyday speeds, but becomes significant as velocities approach the speed of light. Relativity of simultaneity has concrete consequences beyond thought experiments. In particle accelerators, for instance, particles moving close to the speed of light experience different orderings of events than the laboratory frame. This must be accounted for when synchronizing detectors or interpreting collisions. In the Global Positioning System, satellites orbiting Earth operate in a different frame from receivers on the ground. While time dilation effects are the more commonly discussed relativistic correction, relativity of simultaneity also plays a role in ensuring the satellite clocks are properly synchronized with Earth-based systems. Without these corrections, GPS errors would accumulate rapidly, making the system unusable for precise navigation. Einstein himself illustrated the concept with a story involving trains and embankments, but the principle applies universally. Consider two explosions in deep space, separated by millions of kilometers. An astronaut drifting midway between them at rest, relative to the midpoint, will call them simultaneous if the light from both arrives at the same moment. Another astronaut moving rapidly toward one and away from the other will receive the light from the nearer explosion first, leading to the conclusion that it happened earlier. Neither astronaut is wrong, because earlier and later are not absolute labels. They depend on the geometry of space-time and the observer's motion within it. This relativity of simultaneity forces a re-evaluation of the idea of a universal now. In Newtonian physics, the universe could be thought of as a sequence of perfectly synchronized moments, a grand cosmic clock ticking everywhere in unison. In relativity, that clock dissolves into a patchwork of overlapping, frame-dependent slices through space-time. The ordering of events that are separated in space but not causally connected can shift depending on your motion. Only for events that can influence one another, those connected by signals traveling at or below the speed of light, is the order preserved for all observers. The implications are not merely philosophical. The relativity of simultaneity means that in certain configurations, different observers can disagree about whether event A caused event B, as long as the events are outside each other's light cones. This does not lead to paradoxes, because causality is still preserved for events that can influence one another. But it does mean that our intuition about the temporal structure of reality, built from low-speed local experience, is inadequate for describing the universe at large. In the realm of astrophysics, the principle can play a subtle role in interpreting signals from distant sources. When measuring the arrival times of pulses from pulsars or the sequence of flares from active galactic nuclei, the frame of reference matters. Observers moving differently relative to these sources may record different timings and must transform between frames to compare results meaningfully. Relativity of simultaneity also underlies the concept of the block universe in relativity, the idea that past, present, and future all coexist in a four-dimensional spacetime, with now being merely a slice chosen by an observer's state of motion. While not a requirement of relativity, this interpretation gains plausibility from the fact that simultaneity is not universal. If there is no single, agreed-upon present, then it becomes tempting to think of all moments as equally real, their differences only a matter of perspective. From a practical standpoint, technologies that depend on high-precision timekeeping must take the relativity of simultaneity into account. In telecommunications, coordinating signals between moving platforms, such as satellites, aircraft, or deep space probes, requires relativistic corrections to ensure that transmissions arrive and are interpreted in the intended sequence. The same applies in scientific experiments involving widely separated detectors, such as neutrino observatories or gravitational wave detectors, where timing differences of milliseconds can carry significant physical meaning. Experimental verification of the relativity of simultaneity is subtle because the effect is intertwined with time dilation and length contraction. However, experiments that measure the synchronization of moving clocks indirectly confirm the principle. The success of special relativity as a whole, validated by countless tests, leaves little doubt that simultaneity is relative. High-energy physics laboratories regularly work in regimes where the effect is essential to interpreting results correctly. The idea that now is not absolute but depends on the observer's motion is one of those insights that seems almost poetic in hindsight. It tells us that the present is not a rigid frontier between past and future, but a flexible concept that bends and tilts depending on your path through the cosmos. For most of human experience, these tilts are imperceptible, drowned out by the slowness of our motion compared to light. But the universe, in its larger and faster scales, keeps no single clock for us all. And here is where the existential reflection quietly creeps in. If there is no universal present, then the simultaneity we share with others, the moments we call now together, are fragile alignments in the geometry of space-time. They are coincidences born of shared motion, destined to drift apart with separation. In a way, every shared moment is as precious and transient as a flash of lightning on a moving train, seen together only because, for a brief time, our journeys through space and time happen to align. Chapter 3. Gravitational Redshift. When gravity changes the color of light. One of the subtler yet most profound predictions of Einstein's general theory of relativity is that gravity affects not only the motion of matter, but also the passage of light. While we often think of light as something untouchable, immune to the influences that act on planets or falling apples, relativity shows that light, too, must respond to the curvature of spacetime. Gravitational redshift is the name given to one manifestation of this effect, the change in the frequency of light as it climbs away from a gravitational field. In essence, when light escapes from a region of stronger gravity, its wavelength becomes longer, shifting toward the red end of the spectrum. This is not because the light slows down. In a vacuum, it always travels at the same speed, but because the energy it carries is subtly altered by the geometry of spacetime itself. The concept is best understood by stepping back to a key idea in general relativity. Gravity is not a force pulling on objects, but the warping of spacetime by mass and energy. Clocks run at different rates, depending on their position in this curved spacetime, ticking more slowly in stronger gravitational fields. This is gravitational time dilation, and gravitational redshift is in many ways its twin. If time runs slower in a deep gravitational well, then processes that depend on time, such as the oscillations of electromagnetic waves, also appear slower when viewed from outside that well. From the perspective of a distant observer, the peaks and troughs of the wave are stretched apart, resulting in a lower frequency and a longer wavelength. Einstein recognized this connection as early as 1911, before he had fully developed the mathematical framework of general relativity. Working from the equivalence principle, the idea that the effects of gravity and acceleration are locally indistinguishable, He reasoned that a beam of light sent upward in a gravitational field would be observed to lose energy. Since the speed of light must remain constant, the loss of energy would manifest as a change in frequency. Higher frequency corresponds to higher photon energy, and so the photons arriving at a higher point in the gravitational field would appear redshifted. This was a direct consequence of the notion that gravity affects all forms of energy, including light. One way to picture the effect is to imagine light as a stream of tiny energy packets, photons, emitted by an atom deep within a gravitational well. Each photon leaves with a specific energy set by the atom's internal processes. But as the photon climbs out of the gravitational field, it must do work against the curvature of space-time. The result is that by the time it reaches an observer farther from the massive body, its energy is reduced. Because photon energy is tied to frequency, this loss manifests as a shift toward lower frequencies, or redshift. Importantly, this is not a friction-like process. The photon is not slowed or degraded in the conventional sense. The change is a matter of perspective between different gravitational potentials. Gravitational redshift remained a theoretical prediction for decades until experiments could measure it with sufficient precision. One of the landmark tests came in 1959, when Robert Pound and Glenn Rebka at Harvard University used gamma rays emitted from iron-57 nuclei to measure the effect over a height of just 22.5 meters in a tower. By directing the gamma rays upward and detecting their frequency shift, they confirmed the predictions of general relativity within a few percent. Later refinements improved the precision, but the essential results stood firm. Gravity really does change the color of light. In astronomical settings, gravitational redshift is more dramatic. Light escaping from the surface of a massive star, such as a white dwarf, is measurably redshifted. The first detection of this kind came in 1925, when Walter Adams observed the spectrum of Sirius B, a dense white dwarf companion to the bright star Sirius. The shift in spectral lines matched the prediction from general relativity, providing one of the earliest astrophysical confirmations of the theory. In even more extreme environments, such as neutron stars or near the event horizon of a black hole, the redshift can be enormous. For light emitted just outside a black hole's horizon, the effect becomes so strong that to a distant observer the light is stretched infinitely and fades away, a manifestation of the fact that time itself appears to stop at the horizon. Modern technology must also contend with gravitational redshift in more down-to-earth contexts. The satellites in the Global Positioning System orbit at altitudes where Earth's gravitational field is slightly weaker than at the surface. As a result, their onboard atomic clocks tick faster than identical clocks on the ground. While this is often discussed as a time dilation effect, it is the same underlying phenomenon as gravitational redshift. If the signals from these clocks were not corrected for this difference, GPS positions would drift by kilometers within a day. Similar considerations apply to other satellite navigation systems, deep space probes, and any precise timekeeping network spanning regions of different gravitational potential. The universality of gravitational redshift, the fact that it affects all forms of electromagnetic radiation in exactly the same way, is a consequence of the equivalence principle. Regardless of wavelength, from radio waves to gamma rays, the shift depends only on the difference in gravitational potential between the source and the observer. This is why the effect can be used as a diagnostic tool in astrophysics. By measuring the redshift of spectral lines from a star or galaxy, astronomers can infer the depth of its gravitational well and, by extension, its mass and compactness. This gravitational redshift is distinct from the cosmological redshift caused by the expansion of the universe and from Doppler shifts due to relative motion, though in real observations, these effects often occur together and must be disentangled. One particularly elegant demonstration of gravitational redshift comes from binary pulsar systems, where a neutron star orbits a companion. As the neutron star moves toward and away from us in its orbit, its light is Doppler shifted, but superimposed on this is a constant gravitational redshift from the star's immense gravity. By carefully modeling the spectrum, astronomers can measure both the orbital motion and the gravitational potential, leading to precise tests of relativistic gravity in strong field regimes. In laboratory settings, advances in atomic clocks have made it possible to detect gravitational redshift over vertical distances of less than a meter. Clocks based on optical transitions in atoms, such as strontium or ytterbium, are so precise that lifting one to a shelf above another will produce a measurable frequency difference. This extraordinary sensitivity not only tests relativity, but also opens the door to new geophysical techniques, such as using clock networks to measure variations in Earth's gravitational potential caused by tides, groundwater changes, or tectonic activity. Theoretical work has also extended the concept into regimes where quantum mechanics and gravity overlap. For example, experiments with cold atoms have shown that the frequency shift applies not only to light, but also to matter waves. In these cases, the de Broglie frequency associated with the atoms shifts as they move through gravitational fields, an effect that is mathematically analogous to gravitational redshift. This cross-pollination of concepts reinforces the idea that time dilation and redshift are different expressions of the same underlying geometry of space-time. Gravitational redshift is thus more than a curiosity. It is a bridge between the physics of the very large and the very precise. It reveals that the fabric of reality is not uniform but varies with position in a gravitational field, altering the flow of time and the energy of light in perfect synchrony. Its measurement has become a routine tool in astrophysics, a critical correction in engineering, and a sensitive probe in fundamental physics. There is also a conceptual beauty in the way it blurs the line between motion and gravity. Through the equivalence principle, we can think of gravitational redshift as the same effect you would experience in an accelerating rocket. Light sent from the rear to the front of the rocket will be redshifted because, during the transit, the front end accelerates away from the wave fronts. This symmetry between acceleration and gravitation is one of the most elegant aspects of relativity, and gravitational redshift is one of its clearest, most tangible expressions. And yet, for all its precision and predictability, gravitational redshift carries with it a quiet philosophical whisper. If time itself flows differently in different places and the energy of light changes to match, then the universe is not bound together by a single, uniform rhythm. What we call now and what we call energy are not fixed, universal quantities, but local truths woven into the particular patch of space-time we occupy. In that sense, every beam of light is not just a messenger from its source, but a subtle record of the gravitational journey it has taken, a journey that, like our own through life, is shaped by the invisible curves and depths of the world around us. Chapter 4. The Cosmological Constant, Einstein's Biggest Blunder. In 1915, Albert Einstein presented his general theory of relativity a new and revolutionary description of gravity in which mass and energy curve the fabric of space-time, and the motion of objects follows the geometry of that curvature. The equations he formulated were elegant yet flexible, capable of describing a wide variety of possible universes. But when Einstein applied them to the cosmos as a whole, something about the solutions troubled him. According to his new theory, the gravitational attraction of matter should cause the universe to collapse in on itself over time. Yet, like most scientists of his era, Einstein assumed that the universe was eternal and static, unchanging on the largest scales. This was not a conclusion he was willing to challenge in 1917, so he began to look for a way to modify his equations to hold the universe in place. The modification took the form of an additional term in the field equations of general relativity, now called the cosmological constant. Mathematically, it acted like a repulsive force that counterbalanced the attraction of gravity on large scales. The larger the cosmological constant, the more it pushed space-time apart. By tuning its value precisely, Einstein could achieve a static universe, one in which the gravitational pull of matter was exactly offset by this new term. In his view, the cosmological constant was not an arbitrary trick, but a necessary part of the theory if the universe was to remain in equilibrium. For several years, this static solution seemed reasonable. Astronomers at the time lacked any evidence that the universe was expanding or contracting, and the notion of a cosmos fixed in time felt intuitively right. But in 1929, Edwin Hubble announced results that would overturn that picture. By measuring the redshift of light from distant galaxies and comparing it to their apparent distances, Hubble found that galaxies were receding from us, and the farther away they were, the faster they moved. This was not a localized phenomenon. It was evidence that space itself was expanding. Hubble's observations matched predictions that had been made independently by Alexander Friedmann and George Lemaitre, who had solved Einstein's equations without the cosmological constant and found that an expanding or contracting universe was a natural outcome. Upon hearing of the expansion, Einstein reportedly abandoned the cosmological constant, calling it his biggest blunder. The phrase's exact wording is uncertain. Some historians suspect it may have been paraphrased by George Gamow, who claimed Einstein used those words in conversation, but the sentiment is consistent with his reaction. The extra term had been introduced to maintain a false assumption about the cosmos. If he had trusted his equations without that modification, Einstein might have predicted the expansion of the universe more than a decade before it was observed. Yet the story of the cosmological constant did not end there. While it was sidelined for much of the 20th century, some theorists kept it in mind as a general feature allowed by relativity. The constant's effect could be interpreted as a property of empty space itself, giving the vacuum an energy density that exerted a repulsive influence on the geometry of space-time. This vacuum energy idea would later gain support from developments in quantum field theory, where even empty space is filled with fluctuating fields that contribute to its energy content. In the late 1990s, the cosmological constant staged an unexpected comeback. Two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were studying Type 1a supernovae as standard candles to measure the expansion history of the universe. They expected to find that the expansion was slowing down under the pull of gravity. Instead, they discovered that distant supernovae were dimmer than anticipated, implying they were farther away than they would be in a decelerating universe. The only reasonable interpretation was that the expansion of the universe was accelerating. To explain this acceleration, the simplest approach was to reintroduce the cosmological constant into Einstein's equations, this time with a small positive value. Rather than a blunder, the constant now seemed to describe a real, measurable property of the universe, what we now call dark energy. Today, dark energy is estimated to make up about 70% of the total energy content of the cosmos, with the cosmological constant being its simplest possible form. The reinterpretation of Einstein's discarded term as a driver of cosmic acceleration is one of the more ironic turns in the history of physics. It shows how an idea once thought to be a mistake can become central when new evidence emerges. However, the cosmological constant also presents a deep theoretical puzzle. When physicists try to calculate the energy density of the vacuum using quantum field theory, the result is enormously larger than the tiny value implied by cosmological observations, by as much as 120 orders of magnitude. This discrepancy is often described as the worst theoretical prediction in physics, highlighting our incomplete understanding of how quantum mechanics and gravity interact. Despite this challenge, the cosmological constant has become a cornerstone of the standard model of cosmology, known as LCDM, lambda cold dark matter. In this model, lambda represents the cosmological constant, and it works alongside dark matter and ordinary matter to shape the evolution of the universe. Observations of the cosmic microwave background, galaxy clustering, and gravitational lensing all support the existence of this constant or something very much like it. Still, the true nature of dark energy remains one of the great mysteries in science. Is it truly constant, a fixed property of space-time, or could it vary over time and space? Alternative explanations exist. Some theories propose that the acceleration is driven by a dynamic field, often called quintessence, which would change slowly over cosmic time. Others suggest that general relativity itself might need modification on the largest scales, with the apparent acceleration arising from changes to the law of gravity. These models are tested against increasingly precise astronomical surveys, but so far, the simple cosmological constant fits the data remarkably well. From a historical perspective, the saga of the cosmological constant is a reminder that scientific theories are not static. Even within the framework of general relativity, our understanding of the universe has shifted from static to expanding, from decelerating to accelerating, and perhaps, in the future, to something more complex still. Einstein's addition, removal, and the eventual revival of the constant is a vivid example of how scientific ideas can move from the margins to the center of the stage and back again, depending on the evidence at hand. The cosmological constant also illustrates the interplay between theory and observation. Einstein introduced it based on a philosophical preference for a static universe, not an observational need. Later, it was dropped when observations contradicted that preference. Its reappearance came from new data that demanded explanation, even if the solution meant reviving a once rejected idea. This dynamic process, the constant testing, discarding, and reclaiming of concepts, is how science refines its picture of reality. There's a certain humility in recognizing that even Einstein could not anticipate all the consequences of his own theory. His equations contained the seeds of an expanding universe from the start, but his desire for a static cosmos led him to mask that prediction. That same mask, the cosmological constant, now appears to be an essential clue to understanding the fate of the universe. It shapes the very largest scales of space and time, determining whether the cosmos will expand forever, slow to a halt, or meet some other fate. In this sense, the cosmological constant is more than just a parameter in an equation. It is a statement about the nature of the vacuum, about whether space itself is something dynamic and alive with energy. If it is truly constant, the acceleration of the universe will continue indefinitely, leading to a future in which galaxies recede beyond our observable horizon, and the cosmos grows cold and dark. If it is not constant, the story could be stranger still, perhaps reversing into contraction or evolving into states we can barely imagine. And here lies the quiet existential undercurrent. A single term in an equation, once dismissed as a blunder, might determine the ultimate fate of everything. It reminds us that in the vast ledger of the universe, even the smallest entries can have the largest consequences. The cosmological constant is a symbol of how our understanding is always provisional, always open to revision, and of how the cosmos itself may hold surprises that, like this one, wait patiently for us to notice them. Chapter 5. Einstein-Rosen Bridges, the First Theory of Wormholes. In the mid-1930s, Albert Einstein and his collaborator Nathan Rosen set out to address a subtle but profound problem in general relativity. Black holes, though not yet called by that name, had emerged as a possible solution to Einstein's own equations. These solutions, first described by Carl Schwarzschild in 1916, revealed that spacetime could be so warped by mass that nothing, not even light, could escape from a certain boundary, the event horizon. But the Schwarzschild solution contained what appeared to be a singularity, a point of infinite density where the equations themselves broke down. For Einstein, who believed that a complete theory of physics should not require infinities, such singularities were deeply troubling. Einstein and Rosen examined the mathematical form of the Schwarzschild metric and realized something intriguing. The solution could be extended in a way that connected two separate regions of spacetime. In their 1935 paper, they described a structure that joined what we would now call two black holes, or two asymptotically flat universes, through a kind of throat or bridge. This hypothetical structure came to be known as the Einstein-Rosen bridge, and it is the earliest formal description of what popular science today calls a wormhole. The geometry of the Einstein-Rosen bridge was elegant. In essence, the solution replaced the singularity with a smooth connection between two regions, achieved by using a coordinate transformation that doubled the spacetime. From one side of the bridge, gravity would pull inward toward the throat, but instead of terminating in a singularity, the spacetime would open into a mirror image on the other side. The bridge was symmetric. Each mouth led into the other, and the two were connected through a region of extreme curvature. However, Einstein and Rosen did not initially interpret their bridge as a passageway for matter or travelers. Their motivation was to construct a model of particles that avoided singularities. In their view, the bridge could serve as a representation of an elementary particle, with field lines threading through the geometry from one mouth to the other. It was a geometrical solution to a field theory problem, not a proposal for interstellar travel. The popular association between wormholes and faster-than-light shortcuts would come later, as other physicists explored the concept. Mathematically, the Einstein-Rosen bridge is a non-traversable wormhole. In the original formulation using the Schwarzschild solution, the throat connecting the two regions is not stable. It pinches off so quickly that anything attempting to pass through would be crushed or trapped before it could emerge on the other side. This rapid collapse is an unavoidable consequence of the geometry and the causal structure of spacetime in general relativity. To a distant observer, an object approaching the event horizon would appear to slow down and fade away, never quite crossing over. From the infalling object's own perspective, it would encounter the throat only to be destroyed by tidal forces, or to hit the pinch-off before any exit could be reached. The non-traversability of the original bridge does not diminish its importance. The Einstein-Rosen paper opened a line of thought about space-time topology. The idea that the fabric of the universe might be connected in ways that are not immediately obvious from local measurements. Their work demonstrated that general relativity allows for solutions in which distant or even separate regions of the universe are linked directly, without requiring travel through the intervening space. This realization planted the seed for later theoretical developments in wormhole physics, including the search for traversable solutions. In the decades after Einstein and Rosen's work, physicists examined whether modifications to general relativity or the introduction of exotic forms of matter could hold a wormhole open. Exotic matter, in this context, refers to material with negative energy density or unusual pressure properties that violate certain energy conditions in relativity. These conditions, such as the null energy condition, are typically satisfied by all known classical forms of matter and energy. Negative energy densities, however, are not entirely foreign to physics. Quantum field theory predicts effects like the Casimir effect, in which quantum fluctuations create regions of negative energy between conducting plates. Whether such effects could be harnessed to stabilize a wormhole remains a subject of speculation. In 1988, Kip Thorne and his collaborators, Michael Morris and Ulvi Yurtsever, explored the theoretical requirements for a traversable wormhole. Building on the concept introduced by Einstein and Rosen, they proposed metrics that would allow safe passage through a wormhole without encountering singularities or horizons. Their work was motivated in part by science fiction. Carl Sagan had approached Thorne for advice while writing his novel Contact, but it was also rigorous physics. The conditions they found required exotic matter in quantities far beyond anything we can currently produce, as well as precise control over the geometry to prevent instability. Interestingly, wormholes have also been discussed in the context of quantum gravity and the deep structure of spacetime. In some approaches, such as those involving the holographic principle and the ADS-CFT correspondence, wormhole-like connections emerge naturally as part of the mathematical correspondence between different descriptions of a system. In 2013, Juan Maldacena and Leonard Susskind proposed the ER=EPR conjecture, suggesting that Einstein-Rosen bridges, ER and quantum entanglement, EPR, from the Einstein-Podolsky-Rosen paradox might be two sides of the same coin. According to this idea, entangled particles could be connected by microscopic, non-traversable wormholes. While this is still speculative, it reflects the enduring influence of the original 1935 paper in inspiring new lines of thought about the unity of physics. Astrophysically, if wormholes exist on macroscopic scales, they could produce observable signatures. Light passing near the mouth of a wormhole would be gravitationally lensed, much like light around a black hole, but with potentially distinctive patterns due to the connection to another region. Some researchers have proposed that certain gravitational lensing anomalies might hint at wormhole-like structures, though no convincing evidence has been found. The challenge is that the observable behavior of a non-traversable wormhole can closely mimic that of a black hole. making them difficult to distinguish without very precise measurements. The Einstein-Rosen bridge also plays a role in our understanding of black hole interiors. The maximally extended Schwarzschild solution, complete mathematical description of the spacetime around a non-rotating uncharged black hole, contains two asymptotically flat regions connected by a bridge. These regions are often depicted in Penrose diagrams, which compactify spacetime to show causal relationships. In these diagrams, the bridge appears as a fleeting connection that exists only for a moment, collapsing before anything can traverse it. This structure has informed theoretical work on the nature of horizons, singularities, and the ultimate fate of information falling into a black hole. In modern cosmology and high-energy physics, the concept of wormholes has become a testing ground for ideas about the interplay between quantum mechanics and gravity. Even though Einstein and Rosen did not conceive their bridge as a tool for travel, the mathematics they introduced continues to underpin discussions of whether spacetime can have non-trivial topology. Whether in the context of quantum foam at the Planck scale, the possibility of baby universes branching off from our own, or the speculative engineering of exotic matter to stabilize a wormhole, the Einstein-Rosen bridge remains the archetype. From a historical perspective, it is fascinating to see how an idea born from a desire to avoid singularities became an enduring icon in the scientific and cultural imagination. The term wormhole itself would not appear until John Wheeler popularized it in the 1950s, yet the geometry Einstein and Rosen described already contained the essence of the concept. Over time, it has inspired generations of scientists to think about space-time not as a static backdrop, but as something with rich and perhaps playful possibilities for connection. The limitations of the Einstein-Rosen bridge are as instructive as its possibilities. Its non-traversability reinforces the point that general relativity, while generous in allowing unusual geometries, also places strict causal constraints on what can be physically realized. The speed of light limit, the behavior of horizons, and the stability of space-time all conspire to prevent violations of causality. This is not merely a technical inconvenience. It is part of the deep consistency of the theory. Any path toward a traversable wormhole must contend with these constraints, and so far they have proven formidable. Yet even as a purely theoretical construct, the Einstein-Rosen bridge has enriched our understanding of what is possible in the framework of general relativity. It has broadened the conversation about the global structure of space-time, the relationship between geometry and physics, and the ways in which seemingly separate regions might be linked. It has also helped bridge, in the metaphorical sense, the worlds of theoretical physics and public imagination, becoming one of the most recognizable symbols of modern cosmology. And perhaps this is where the existential undertone emerges. The Einstein-Rosen bridge, in its original form, offers no safe passage to distant worlds. It is a connection we can describe but not cross, a reminder that not all doorways are meant to be opened. In the mathematics of space-time, as in life, there are paths that exist only in principle, elegant, compelling, but forever out of reach. They show us the shape of possibility, even if we can never take the journey ourselves. Chapter 6. Frame dragging. When space is twisted by spinning mass. When Albert Einstein formulated general relativity, he replaced the Newtonian picture of gravity as a force with a description of mass and energy bending the geometry of spacetime. In this new view, planets orbit the sun not because they are pulled by an invisible force, but because they move along curved paths in the warped fabric of space and time. This idea has already transformed our understanding in many contexts, but one of its most subtle and fascinating predictions involves what happens when the object doing the warping is not only massive, but also rotating. Rotation changes the way space-time behaves. Just as a moving electric charge generates a magnetic field in addition to an electric field, a rotating mass generates effects beyond the static curvature of space-time. In the same way that electromagnetism has electric and magnetic components, gravity and general relativity has a gravitoelectric component, corresponding to the familiar attraction due to mass, and a gravitomagnetic component, which emerges from the motion of mass. When a massive body spins, it drags the space-time around it into a gentle swirl. This phenomenon is called frame dragging. Frame dragging is not a distortion you could see in the way space appears to the eye, but rather a shift in how space and time are measured by observers. Imagine placing a perfectly free-floating gyroscope far from any massive object. In flat space-time, its axis would continue pointing in the same direction forever. But place that gyroscope near a rotating planet, star, or black hole, and something remarkable happens. Even without any physical torque applied, the axis will slowly precess. This precession is caused by the rotation of space-time itself, as though the grid of space and time coordinates were being twisted by the spinning mass. The exact nature of frame dragging was first worked out in 1918 by Austrian physicists Josef Lenz and Hans Thirring in what is now called the Lenz-Thirring effect. They calculated how the rotation of a spherical mass would influence the motion of orbiting bodies and the orientation of gyroscopes. In their results, any object moving in the gravitational field of a rotating mass experiences a small but measurable change in its motion due to the dragged space-time. For bodies in orbit, this can slightly shift the orientation of the orbital plane over time. On Earth, the effect is extraordinarily small because our planet, though massive by everyday standards, is not massive enough to produce a strong twist in space-time. Detecting frame dragging here requires extremely precise instruments. For decades, the most famous attempt was NASA's Gravity Probe B mission, launched in 2004 after decades of development. The spacecraft carried ultra-precise gyroscopes, spheres polished so perfectly that they deviated from a perfect sphere by less than 40 atomic layers. These gyroscopes were placed in a nearly frictionless suspension and pointed toward a guide star. Over the course of a year, the spacecraft measured the tiny drift in their orientation caused by two relativistic effects: the geodetic effect, space-time curvature due to Earth's mass, and the frame dragging effect, twist, due to Earth's rotation. The measured frame dragging precession matched general relativity's predictions to within about 19%, a remarkable confirmation given the experimental difficulty. Other experiments have detected frame dragging indirectly by studying the orbits of satellites such as Lagios and Laris, which are tracked with laser ranging to millimeter precision. Over time, their orbital nodes, the points where the orbit crosses Earth's equatorial plane, slowly shift due to frame dragging. These measurements are complicated by the need to account for other sources of orbital perturbation, such as the uneven distribution of Earth's mass and the gravitational influence of the Moon and Sun, but careful modeling has produced results consistent with relativity. In stronger gravitational environments, frame dragging becomes much more dramatic. Near a rotating black hole, described by the Kerr solution to Einstein's equations, The twisting of space-time is so extreme that it produces a region called the ergosphere. Within the ergosphere, frame dragging is unavoidable. Space and time are dragged around the black hole faster than any observer could resist. In this region, it is impossible to remain stationary relative to the distant universe. Everything must co-rotate with the black hole's spin. This has fascinating consequences, including the possibility of extracting energy from the rotation through processes such as the Penrose process, in which particles can leave the ergosphere with more energy than they entered. The twisting of space-time near such objects also affects the paths of light. Photons traveling close to a rotating black hole will have their trajectories bent not only by the curvature of space-time, but also swirled by the frame dragging. This effect alters the appearance of the accretion disks around these black holes, changing the way we observe their light. Recent simulations used to interpret images from the Event Horizon Telescope include frame dragging as an essential ingredient in predicting what the surroundings of a rotating black hole look like. Frame dragging also plays a role in astrophysical jets, the enormous, narrow beams of plasma launched from the regions near supermassive black holes in active galaxies. While the full mechanism behind these jets involves magnetic fields and accretion disk physics, frame dragging can help twist and collimate the magnetic field lines, channeling energy outward along the rotation axis of the black hole. This way, a process originating in the geometry of spacetime itself may influence structures stretching across thousands of light years. In neutron stars, which can rotate hundreds of times per second, the combination of intense gravity and rapid spin makes frame dragging far stronger than near Earth. This can affect the oscillation frequencies of matter in the star's vicinity, influencing phenomena such as quasi-periodic oscillations in X-ray binaries. Studying these effects provides a way to probe both the rotation rates and the internal structure of these exotic objects. From a theoretical standpoint, frame dragging is a vivid example of how general relativity unifies space and time into a single fabric. Rotation in space is inseparable from its influence on time, and the frames in frame dragging refer to the coordinate systems attached to observers moving through spacetime. When mass rotates, it carries these frames with it, a reminder that space and time are not passive backgrounds, but dynamic participants in the physics of the universe. There is a conceptual parallel here to Mach's principle, an idea that influenced Einstein during the development of general relativity. Mach's principle suggests that the local inertial frames we experience are determined in some way by the distribution and motion of mass throughout the universe. While general relativity does not fully embody Mach's principle, frame dragging can be seen as a concrete realization of part of its spirit. The rotation of a massive body affects the inertial frames in its vicinity. Detecting and studying frame dragging is not merely a test of relativity. It also refines our understanding of gravitational interactions in complex systems. As gravitational wave astronomy matures, the influence of frame dragging in the dynamics of merging neutron stars and black holes becomes an observable signal. The spin of the components leaves imprints on the waveform that can be measured, allowing astronomers to deduce rotational properties of objects that are otherwise invisible. Even in the relatively weak gravitational field of Earth, accounting for frame dragging is essential in certain precise measurements. Experiments involving ring laser gyroscopes and atom interferometers, which can detect minute rotational effects, are pushing the boundaries of sensitivity. As technology improves, we may be able to measure frame dragging in new contexts, perhaps even using quantum sensors that combine the precision of atomic clocks with interferometric techniques to detect changes in space-time geometry. The deeper we study frame dragging, the clearer it becomes that it is not an exotic side effect of relativity, but a fundamental feature of rotating spacetimes. It shows us that the geometry of the universe is not static, but can be set into motion by the matter it contains. It blurs the intuitive line between rotation in space and rotation of space itself, forcing us to rethink what it means to move, to be stationary, or to remain fixed relative to the cosmos. And as with many of Einstein's insights, there is a quiet philosophical undertone here. If even the fabric of space and time can be twisted by motion, then the universe is far from the rigid stage we once imagined. It is more like a vast ocean where massive bodies spin and stir the currents of reality itself. And we, small as we are, move within these currents, perhaps unaware of the subtle swirls shaping our journey, yet carried along by them all the same. Chapter 7. Bose-Einstein Condensate, a New State of Matter. In the early decades of the 20th century, quantum mechanics was still taking shape, and its implications for the behavior of matter were only beginning to be understood. Among the revolutionary ideas to emerge was the concept of a completely new state of matter, one that could only exist under extraordinary conditions. This idea originated in 1924 when Indian physicist Satyendra Nath Bose developed a novel way to describe the statistical behavior of particles of light, or photons. His work addressed a problem in Planck's theory of blackbody radiation, offering a method for counting photon states that matched experimental results. When Bose sent his paper to Albert Einstein for review, Einstein recognized its significance immediately and translated it into German for publication in Zeitschrift für Physik. Einstein saw that Bose's statistical method did not just apply to photons, but could also describe massive particles with integer values of spin, particles we now call bosons in Bose's honor. This was a departure from the statistics governing fermions, which have half-integer spin and obey the Pauli exclusion principle, forbidding them from occupying the same quantum state. Bosons, by contrast, are gregarious in the quantum sense. There is no limit to how many of them can share the same state. This simple fact hinted at the possibility of collective behavior on a scale never seen before in ordinary matter. Einstein extended Bose's work to predict what would happen to a dilute gas of bosonic atoms cooled to temperatures near absolute zero. At such low energies, the thermal motion of the atoms would slow dramatically, and their individual wave functions, the quantum descriptions of their states, would spread out. Eventually, at a critical temperature, these wave functions would overlap to the point that the atoms would lose their individual identities. They would all collapse into the same lowest energy quantum state, behaving not as separate particles, but as a single coherent quantum entity. Einstein predicted that this new state of matter, later called a Bose-Einstein condensate, BEC, would have unique properties distinct from solids, liquids, gases, and plasmas. For decades, the prediction remained purely theoretical. Cooling atoms to such low temperatures was far beyond the technology of the early 20th century. Progress in cryogenics and laser cooling techniques gradually brought the possibility closer. Laser cooling works by using photons tuned to slightly below an atomic transition frequency. When atoms move toward the laser source, they preferentially absorb photons, which slows them down. Combined with magnetic trapping and evaporative cooling, This method allows atoms to reach nanokelvin temperatures, just billionths of a degree above absolute zero. In 1995, more than 70 years after Einstein's prediction, Eric Cornell and Carl Wieman at the University of Colorado Boulder succeeded in creating the first gaseous Bose-Einstein condensate using rubidium-87 atoms. Within months, Wolfgang Ketterl at MIT produced a BEC with sodium atoms that was larger and longer lived, allowing for more detailed study. The Nobel Prize in Physics in 2001 was awarded to Cornell, Wieman, and Ketterl for their pioneering work. The achievement was a milestone in experimental physics, demonstrating that quantum mechanical effects could be observed and manipulated on macroscopic scales. A Bose-Einstein condensate is strikingly different from any other phase of matter. In a normal gas, the atoms move in random directions at a range of speeds. In a BEC, all atoms move in unison, described by a single macroscopic wave function. This coherence gives rise to properties such as superfluidity, the ability to flow without viscosity. In superfluid helium, a related but distinct phenomenon, liquid helium-4 cooled below 2.17 K can climb container walls and pass through tiny pores without friction. In dilute atomic BECs, superfluidity manifests in features like quantized vortices, where rotation occurs only in discrete steps determined by quantum mechanics. The coherence of a BEC also makes it an extraordinary laboratory for exploring fundamental physics. Because the atoms share one quantum state, they can exhibit interference patterns much like coherent light beams in a laser. In fact, BECs are sometimes called atom lasers when manipulated to emit coherent matter waves. These matter waves can be used in precision measurements, such as interferometry experiments that test aspects of general relativity or search for tiny variations in fundamental constants. BECs have also been used to simulate conditions in other physical systems that are difficult to study directly. For example, researchers can adjust the interactions between atoms in a condensate using a technique called a Feshbach resonance, in which an external magnetic field changes the effective scattering length between particles. By tuning these interactions, scientists can mimic phenomena from condensed matter physics, such as superconductivity, or explore exotic phases of matter that may exist inside neutron stars. Another fascinating property of BECs is the ability to slow light to extremely low speeds. In 1999, Lien Hao and her colleagues demonstrated that by passing light pulses through a sodium condensate under specific conditions, the group velocity of light could be reduced to just a few meters per second. This control over light-matter interaction is not merely a curiosity. It has potential applications in quantum information processing, where storing and retrieving light pulses could form the basis for quantum memory devices. The creation of BECs in space has opened yet another frontier. In 2018, NASA's Cold Atom Laboratory aboard the International Space Station produced BECs in microgravity, where they can be observed for longer times without the atoms falling under Earth's gravity. This environment allows for experiments that probe the delicate dynamics of condensates with unprecedented precision, potentially leading to new insights in both fundamental physics and practical technology. While Bose-Einstein condensates are composed of bosons, there is an intriguing connection to systems made of fermions. Through pairing mechanisms, such as those that occur in superconductors where electrons form Cooper pairs, fermions can effectively behave as composite bosons and condense into similar macroscopic quantum states. This crossover between Bose-Einstein condensation and Bardeen-Cooper-Schrieffer BCS superconductivity has been explored in ultra-cold atomic gases, revealing a continuous transition between the two regimes and deepening our understanding of strongly interacting quantum systems. Studying BECs also challenges our intuition about the boundary between the quantum and classical worlds. We are accustomed to thinking of quantum effects as confined to microscopic particles, but a condensate can be visible to the naked eye, with millions or billions of atoms behaving in perfect unison. This macroscopic quantum state invites questions about decoherence, the process by which quantum systems lose their coherence through interaction with the environment. Understanding how BECs maintain coherence and how it can be controlled or extended is essential for future quantum technologies. Despite their fragility, condensates have proven to be versatile platforms for exploring complex physics. They can host solitons, stable, localized waves that maintain their shape during propagation, and vortices that mimic the behavior of cosmic strings predicted in certain models of the early universe. By adjusting trap geometries, interactions, and external fields, researchers can create analogs of phenomena from high-energy physics, astrophysics, and cosmology, all within the confines of a laboratory. The realization of Bose-Einstein condensation was a direct vindication of a theoretical prediction made when quantum mechanics was still young. It also stands as a testament to the interplay between theory and experiment. Bose's statistical reasoning, extended by Einstein's insight into massive particles, remained an untested idea for generations, waiting for experimental tools to catch up. When they finally did, the result was not just the confirmation of a prediction, but the opening of an entirely new domain of matter, with its own rules, behaviors, and potential applications. And there's a quiet philosophical resonance here. In a world where individuality is the norm, the atoms in a Bose-Einstein condensate surrender their separate identities to become part of a greater whole, acting as one. They remind us that under the right conditions, even the smallest parts of nature can merge into unity, a harmony written in the language of quantum mechanics, fleeting but profound, and as delicate as the chill near absolute zero that makes it possible. Chapter 8. Unified Field Theory, Einstein's Unfinished Dream. By the time Albert Einstein published his general theory of relativity in 1915, he had already accomplished what many would consider the pinnacle of a scientific career. He had redefined gravity, not as a mysterious force acting at a distance, but as the curvature of space-time produced by mass and energy. Yet Einstein did not regard this as the end of his quest for understanding. For him, general relativity was a towering achievement, but also an incomplete chapter in the book of nature. He wanted more than a theory of gravity. He wanted a single, all-encompassing framework, a unified field theory that would weave all the fundamental forces of nature into one coherent mathematical structure. In the early 20th century, two great pillars of physics stood apart. General relativity described gravity on cosmic scales, explaining planetary orbits, the bending of light near stars, and the dynamics of the expanding universe. Electromagnetism, codified in Maxwell's equations, described the behavior of electric and magnetic fields, unifying them into a single force and explaining light itself as an electromagnetic wave. Both were extraordinarily successful in their own domains, but they spoke different mathematical languages. Gravity was geometry, curved space-time, while electromagnetism was expressed through field equations in flat space-time. Einstein's dream was to bring them under one roof. He was not the first to imagine such unification. Theodore Kaluza had already proposed in 1921 that by extending general relativity to a fifth dimension, one could naturally incorporate Maxwell's equations into the same mathematical structure that described gravity. Oscar Klein later refined this idea by suggesting that the extra dimension could be compactified, curled up so tightly that it would be imperceptible at human scales. Kaluza-Klein theory was elegant but speculative, and it lacked experimental support. Still, it hinted at a path toward unification that Einstein would explore repeatedly in the decades that followed. Einstein's efforts took many forms over the years. He investigated extensions of general relativity that altered the geometry of space-time itself, introducing asymmetric connections and non-symmetric metrics that might encode both gravitational and electromagnetic fields. He experimented with teleparallel formulations in which gravity could be described by torsion rather than curvature, hoping that this alternative geometry might leave room for electromagnetism to fit naturally. These approaches were mathematically rich, but each faced the same obstacle. They failed to reproduce known particle physics in a convincing way, and they offered no new predictions that could be tested to confirm or falsify the theory. Part of the difficulty was historical timing. By the 1920s and 1930s, quantum mechanics had emerged as the framework for understanding atomic and subatomic phenomena, including electromagnetism at the particle level through quantum electrodynamics. Einstein, however, remained deeply skeptical of the probabilistic nature of quantum theory. His discomfort with quantum mechanics, particularly its apparent randomness, meant that he sought a deterministic unification, a theory in which both gravity and electromagnetism would emerge from continuous, smooth fields without resorting to discrete quantum jumps. This philosophical stance put him increasingly at odds with the mainstream direction of physics, which embraced quantum theory's statistical character and moved on to develop quantum field theories for the electromagnetic, weak, and strong nuclear forces. Still, Einstein persisted. His unified field theory attempts often involved intricate tensor mathematics, producing elaborate systems of equations that he hoped would yield both gravitational and electromagnetic solutions. Sometimes these models could be made to resemble known physical laws under certain approximations, but they tended to lack the flexibility to describe the full variety of matter and forces observed in nature. Without the incorporation of quantum mechanics, they were also incomplete by design, unable to capture the inherently quantum behavior of electrons, photons, and other particles. As the decades passed, the gap between Einstein's program and the rest of the physics community widened. While he pursued geometric unification, other physicists were building the foundations of the standard model of particle physics, a quantum framework uniting electromagnetism with the weak and strong nuclear forces, leaving gravity as the outlier. The standard model's success in predicting and explaining experimental results, from the existence of new particles to the behavior of high-energy collisions, made Einstein's classical, geometry-only approach seem increasingly disconnected from the pressing questions of the day. Yet, despite its isolation from mainstream research, Einstein's quest was not fruitless. Many of the mathematical structures he explored would later reappear in other contexts. Ideas about extra dimensions, for example, would become central to string theory decades later, where additional spatial dimensions help unify all forces, including gravity, in a quantum-consistent way. Teleparallel gravity, once a niche offshoot of Einstein's thinking, continues to be studied as an alternative formulation of general relativity. and the very notion of a unified field remains a guiding aspiration in theoretical physics, even if the route to achieving it looks very different from the one Einstein envisioned. In the years before his death in 1955, Einstein continued to publish on unified field theories, working largely alone at Princeton's Institute for Advanced Study. His last scientific papers still wrestled with the problem, seeking equations in which matter might emerge as a manifestation of field singularities rather than as something added by hand. There was a kind of poetic symmetry to his persistence, the same drive that had carried him from the special relativity of 1905 to the general relativity of 1915. The belief that nature's laws are unified and deeply interwoven never left him, even as the physics world moved in other directions. In hindsight, Einstein's unified field theory work can be seen as a transitional phase in the larger human effort to understand the fundamental forces. His reluctance to engage fully with quantum mechanics meant that his specific models were unlikely to succeed in describing reality as we know it. But the philosophical motivation that there should be a single, coherent description of all physical phenomena remains one of the most powerful ideas in science. Today's searches for quantum gravity, string theory, loop quantum gravity, and other theories of everything can be seen as descendants of the same ambition. One might also note the curious reversal in perspective that history has brought. Einstein introduced the cosmological constant to general relativity and later discarded it, calling it a blunder, only for it to return as a key part of modern cosmology. Similarly, while his specific unified field equations did not survive, the quest for unification has returned to prominence, though now grounded in a framework that unites quantum theory with relativity rather than opposing them. The challenge Einstein faced remains with us. Gravity, described so well by general relativity, and the other three fundamental forces, described by quantum field theory, do not yet fit together into a single consistent framework. We can describe each domain with exquisite accuracy, but at the Planck scale, where quantum effects of gravity should be important, our theories clash. This is the frontier Einstein wanted to cross, and though he did not succeed, he left behind the conviction that such a crossing is possible. And perhaps there is an existential thread here too. The dream of a unified field theory is a reflection of a deeper human desire, the belief that the world, in all its complexity, springs from a single, comprehensible order. It is the hope that beneath the surface differences there is a hidden simplicity waiting to be revealed. For Einstein, that unity was not just a scientific goal, but a philosophical necessity. And even though the exact form of that unity remains unknown, his pursuit reminds us that some journeys are worth taking, even if they extend far beyond a single lifetime. Chapter 9. The EPR Paradox, Einstein's Quantum Challenge. By the 1930s, quantum mechanics had already proven itself as one of the most successful theories in the history of science. It explained the structure of atoms, the stability of matter, and the behavior of light and electrons in ways that no classical theory could match. Its predictions had been verified with unprecedented precision. Yet for all its successes, quantum mechanics carried with it a conceptual strangeness that troubled even some of its founders. Chief among them was Albert Einstein, who had himself played a crucial role in launching the quantum revolution through his explanation of the photoelectric effect and his work on the quantization of energy. Despite this, Einstein was deeply dissatisfied with the way quantum mechanics seemed to abandon determinism and replace a fully knowable reality with probabilities and wave functions. For Einstein, physics was not just about predicting outcomes. It was about describing an objective reality that exists independently of observation. The prevailing interpretation of quantum mechanics in the 1920s and 1930s, known as the Copenhagen interpretation and championed by Niels Bohr and Werner Heisenberg, suggested that certain properties of a quantum system do not have definite values until they are measured. In this view, the act of measurement plays a fundamental role in bringing about the outcome, and the wave function is not a description of a hidden reality, but rather a tool for calculating probabilities. Einstein's discomfort with this viewpoint was not mere philosophical stubbornness. He believed that if quantum mechanics was correct as it stood, it implied that the world was non-local. That is, events in one place could instantaneously affect events in another, without any signal traveling between them through space. This seemed to contradict special relativity, which held that nothing could travel faster than the speed of light. In his view, if quantum mechanics required such instantaneous influence, then it was incomplete. There had to be deeper, as yet undiscovered variables, hidden variables, that would restore a fully local and deterministic description of the world. In 1935, Einstein, working with Boris Podolsky and Nathan Rosen, set out to formalize this critique in a paper published in the journal Physical Review. The paper presented a thought experiment that came to be known as the Einstein-Podolsky-Rosen paradox, or EPR paradox. The goal was to show that the quantum mechanical description of reality as formulated at the time could not be both complete and consistent with the principle of locality. The setup of the EPR thought experiment involves two particles that interact in such a way that their properties become correlated, what we now call quantum entanglement. For example, the total momentum of the two particles might be precisely known and equal to zero, or their positions might be linked in a definite way. According to quantum mechanics, after the interaction, the particles can be separated by an arbitrary distance, yet the correlation persists. If you measure the position of one particle, you instantly know the position of the other. If you measure the momentum of one, you instantly know the momentum of the other. Einstein, Podolsky, and Rosen argued that this led to an unavoidable conclusion. Either the measurement on one particle instantly affected the state of the other, no matter how far apart they were, or the particles carried with them predetermined values for these quantities, values not contained in the wave function. In the first case, you had spooky action at a distance, something Einstein found unacceptable. In the second, the wave function was incomplete. It did not contain all the information about the system, and some underlying reality must exist that quantum mechanics failed to describe. Their paper concluded that the second option was the reasonable one. Quantum mechanics was a useful tool, but not the final word. Niels Bohr's reply to EPR was characteristically subtle. He argued that the EPR authors misunderstood the nature of quantum measurements and the role of complementarity, the idea that certain pairs of properties, like position and momentum, cannot be simultaneously defined with arbitrary precision. For Bohr, the correlations predicted by quantum mechanics did not require any signal or influence traveling between the particles. Instead, the act of measurement defined the conditions under which statements about physical quantities could be made. The apparent instantaneous connection was not a transfer of information in the classical sense, but a reflection of the holistic nature of the quantum state. For decades, the debate remained largely philosophical. The mathematical formalism of quantum mechanics was unchallenged, and the EPR paradox seemed impossible to test experimentally because it involved subtle correlations that would be exceedingly difficult to measure. That began to change in the 1960s when physicist John Bell derived a theorem that made the issue testable. Bell showed that any local hidden variable theory, any theory in which measurement results are determined by pre-existing properties that do not allow faster-than-light influences, must satisfy certain mathematical inequalities, now known as Bell inequalities. Quantum mechanics, by contrast, predicts situations in which these inequalities are violated. Bell's theorem transformed the EPR paradox from a philosophical challenge into an experimental one. In the following decades, increasingly sophisticated experiments, beginning with those of Albert Einstein in the 1980s, tested Bell inequalities using entangled photons and other systems. The results consistently violated the inequalities, supporting the quantum mechanical predictions and ruling out a broad class of local hidden variable theories. More recent experiments have closed various loopholes, potential ways in which hidden variables might still account for the results, using entangled particles over large distances, high-efficiency detectors, and fast switching of measurement settings. The conclusion is now widely accepted. If quantum mechanics is correct, nature is non-local in the specific sense that entangled particles exhibit correlations that cannot be explained by any local hidden variable theory. From the standpoint of physics, this does not mean that information or matter travels faster than light in a way that could be used for communication. Relativity remains safe from contradiction. The correlations are instantaneous, but they cannot be used to send a signal. Instead, the EPR paradox and the experimental violations of Bell inequalities tell us that the quantum world does not fit into the classical framework of local realism. The combination of the ideas that physical properties exist independently of observation and that influences cannot travel faster than light. At least one of these deeply rooted concepts must give way, and quantum mechanics chooses to give up locality in favor of a non-local but causally consistent structure. Today, quantum entanglement, the very phenomenon that Einstein once used as a critique, is seen as one of the most intriguing and useful features of quantum mechanics. It underlies technologies in development such as quantum cryptography, which promises secure communication guaranteed by the laws of physics, and quantum computing, where entanglement between qubits allows for powerful computations that classical computers cannot efficiently perform. In this sense, the EPR paradox has moved from a challenge to the foundations of quantum theory to a cornerstone of practical quantum information science. Still, the philosophical questions raised by EPR continue to fascinate physicists and philosophers alike. What does it mean for two particles to be linked in such a way that measuring one tells you something about the other instantaneously, regardless of the distance between them? Is the wave function a complete description of reality? Or is it a tool for prediction that leaves out deeper structures? Interpretations of quantum mechanics vary widely on these points. The many-worlds interpretation, for example, explains the correlations without non-local influences by positing that all possible outcomes occur in parallel branches of the universe. The Bohemian interpretation embraces non-locality explicitly, with particles guided by a pilot wave that spans space. Relational and information-based interpretations redefine what it means for a property to exist at all. None of these resolves the debate to universal satisfaction. The EPR paradox remains a touchstone in discussions about the meaning of quantum theory because it crystallizes the tension between quantum mechanics and the intuitions inherited from classical physics. It forces us to confront the fact that our deepest assumptions about space, time, and reality itself may need revision. Einstein's challenge, though answered experimentally in favor of quantum mechanics, has left us with an even stranger picture of the world, one in which separation in space does not guarantee independence, and in which the act of measurement is woven into the fabric of reality in ways we still do not fully understand. And here, perhaps, lies the quiet existential echo of the EPR paradox. If the universe allows such connections, invisible threads that bind particles across vast distances, then maybe the separations we perceive are not as absolute as they seem. In a world where even the smallest constituents of matter can remain linked in defiance of distance, perhaps the boundaries we draw, both in physics and in life, are less rigid than we imagine. Chapter 10. Brownian Motion, Proving Atoms Are Real. At the dawn of the 20th century, the atomic theory of matter, the idea that all substances are composed of indivisible microscopic particles, had been proposed for over 2,000 years, dating back to the philosophies of Leucippus and Democritus in ancient Greece. By the 1800s, chemists like John Dalton and physicists like Ludwig Boltzmann had developed it into a coherent scientific framework, one that could explain chemical reactions and the properties of gases. And yet, despite its explanatory power, the existence of atoms was still debated. Some prominent scientists, including the influential physicist-philosopher Ernst Mach, regarded atoms as useful fictions, convenient mathematical devices rather than physically real entities. The difficulty lay in the fact that atoms were far too small to be observed directly with the microscopes of the time. The evidence for their existence came indirectly from the way matter behaved in bulk. For some, this was enough. For others, the lack of direct, indisputable proof left room for skepticism. It would take a phenomenon first observed decades earlier, an odd, jittery movement of tiny particles suspended in a fluid, and the insight of Albert Einstein to provide one of the most compelling demonstrations that atoms are real, tangible objects. The phenomenon in question, Brownian motion, had been named after the Scottish botanist Robert Brown, who in 1827 noticed that pollen grains suspended in water seemed to move in a constant, irregular way under his microscope. The particles did not drift in a single direction, nor did they come to rest over time. Instead, they jittered randomly, as though buffeted by invisible forces. Brown at first suspected that the movement might be a sign of life, but when he repeated the observation with particles of inorganic matter, such as dust, the effect persisted. It was clearly not biological in origin. Over the 19th century, scientists proposed various explanations. Some speculated about convection currents in the water or vibrations from the laboratory environment. Others, particularly those inclined toward atomism, suggested that the motion was due to countless collisions with the water molecules themselves, which were in constant thermal motion. This idea fit neatly with the kinetic theory of gases and liquids, but it was qualitative. Without a rigorous quantitative theory connecting molecular motion to the observed particle movements, the atomic interpretation remained suggestive rather than decisive. In 1905, a year remarkable in Einstein's career for several groundbreaking papers, he turned his attention to Brownian motion. He approached the problem with the tools of statistical mechanics, a framework that links the microscopic properties of atoms and molecules to the macroscopic behavior of matter. Einstein modeled the suspended particles as being bombarded from all sides by the molecules of the surrounding fluid. Because the molecular impacts are random and uncorrelated, the particle's motion becomes a kind of random walk, changing direction and speed with each collision. What made Einstein's analysis powerful was his ability to relate measurable quantities to the underlying atomic parameters. He derived an equation for the mean squared displacement of a particle as a function of time, temperature, the viscosity of the fluid, and the size of the particle. Crucially, the equation also depended on Avogadro's number, the number of molecules in 1 mole of a substance. By observing Brownian motion under a microscope and measuring these displacements, one could determine Avogadro's number experimentally, thereby confirming the molecular nature of matter. Jean Perrin, a French physicist, took up the challenge of testing Einstein's predictions. Over a series of meticulous experiments between 1908 and 1913, Perrin tracked the positions of microscopic particles suspended in liquids, measuring their movements over time and comparing them to Einstein's theoretical values. His results matched the theory closely, allowing him to calculate Avogadro's number with impressive accuracy. Perrin's work earned him the Nobel Prize in Physics in 1926, and it played a decisive role in convincing the scientific community that atoms were not just mathematical abstractions, but physically real. The significance of this achievement went beyond settling an old debate. It provided a direct visual bridge between the microscopic world of atoms and the macroscopic world we experience. By looking through a microscope at tiny specks in constant, random motion, one could literally see the imprint of molecular activity, the ceaseless thermal jostling of trillions of particles that make up the fluid. Brownian motion thus became not only a proof of the atomic hypothesis, but also a vivid illustration of the reality of thermal energy at the molecular scale. Einstein's treatment of Brownian motion also had broader implications for the development of probability theory and the study of stochastic processes. The mathematical description of random walks that emerged from his work would later find applications far outside physics, in fields as diverse as biology, finance, and computer science. Models of stock price fluctuations, the spread of diseases, and the behavior of complex systems often use the same statistical tools that describe the wandering of a pollen grain in water. On a physical level, Brownian motion is a direct consequence of the second law of thermodynamics, the principle that systems tend toward greater entropy or disorder. In a fluid at non-zero temperature, the constituent molecules are in perpetual motion, exchanging energy through collisions. A microscopic particle immersed in this fluid cannot avoid being buffeted by these molecular impacts. Even though the molecules are far too small and fast to be seen individually, their collective effect is observable in the erratic path of the suspended particle. In modern research, Brownian motion remains a subject of interest, both as a phenomenon to be understood in greater detail and as a tool for probing other systems. Techniques such as optical tweezers use tightly focused laser beams to trap and manipulate individual microscopic particles, allowing scientists to study their Brownian motion with extraordinary precision. This, in turn, provides insights into the properties of complex fluids, biological systems, and nanostructures. In the realm of soft matter physics, where systems like polymers, colloids, and gels dominate, Brownian motion is a fundamental mechanism governing how particles diffuse and interact. In living systems, too, Brownian motion plays a vital role. Inside cells, molecules and organelles are constantly in motion, propelled in part by thermal agitation. Diffusion, the process by which substances spread from regions of high concentration to low concentration, is essentially Brownian motion on a molecular scale. The random walk of molecules ensures that nutrients, signaling compounds, and other essentials are distributed throughout the cell, enabling life's chemical machinery to function. The universality of Brownian motion, its appearance in contexts as varied as financial markets, pollen grains, and intracellular transport, underscores the deep connections between seemingly unrelated systems. The same statistical principles that Einstein used to prove the existence of atoms can be applied to understand fluctuations in systems across the natural and social sciences. This is one reason why his 1905 paper on the subject remains a cornerstone in the study of stochastic processes. Looking back, it is striking how a phenomenon that could be observed with the simplest of microscopes became one of the decisive proofs of a fundamental truth about matter. Brownian motion connected the abstract equations of kinetic theory with tangible, visible evidence. For Einstein, it was an opportunity to apply statistical reasoning to bridge the gap between theory and observation. For the broader scientific community, it was a turning point that transformed atoms from a plausible hypothesis into an empirical reality. And perhaps there is a quiet philosophical resonance in this story as well. The restless, ceaseless motion of tiny particles, invisible on their own, yet collectively capable of revealing the underlying structure of reality, mirrors the way knowledge itself advances. Small, seemingly random steps, each insignificant in isolation, can over time lead us to profound truths. Brownian motion is not just a proof of atoms. It is a reminder that the hidden motions of the unseen can shape the world in ways that, with patience and insight, we can eventually discern. And that's where our quiet journey through Einstein's lesser-known ideas comes to an end. If you're still awake, there's another story waiting for you, just a click away. But if your eyes are growing heavy, then may you drift into sweet dreams among the stars.